Hello friends. So, today we start with a new topic, very important topic which has applications in all fields of science and engineering, in the importance or in the nature of prevalence, how prevalent this topic is, finds its usage in different fields. It probably ranks only next to equation solver, solution of simultaneous equations, and what we are referring to is the algebraic eigenvalue problem. And singular value decomposition is a related problem which can be cast as an algebraic eigenvalue problem as well, but it is more efficient to solve in its own formulation. So, let us define what is understood by what is meant by algebraic eigenvalue problem and what it means. So, essentially the algebraic eigenvalue problem is defined as A x is equal to lambda x, where A is a square matrix, x is of course a vector and lambda is a scalar. So, what this means is we are looking for that particular vector x, which when multiplied with a matrix, given matrix A, results in a scaled version of its own self. That is, the vector does not change its direction, it only changes its magnitude. Now, that is a very special property. Normally, when a matrix multiplies a vector, that implies a rotation in plane. So, in this particular case, we are looking for that particular vector for a given matrix, which when multiplied with this matrix does not change its direction, but it only is affected, it only changes its length. So, the whole idea, the formal statement is matrix vector multiplication, that is A times x, results in a scaled version of the same vector. So, lambda times x, lambda is a scalar. A very special results, very special result which holds only for a few select vectors for a given matrix A, and this does not happen for any arbitrary vector if a matrix A is given, and lambda is known as the eigenvalue of this matrix A, and associated with this eigenvalue is the vector x, that is called the eigenvector. So, it is this pair eigenvalue and eigenvector, the computation of this pair of eigenvalue and eigenvector, I mean there can be several such pairs for a given matrix. So, this process of computation of these eigenvalues and eigenvectors is what is referred to as the algebraic eigenvalue problem. Now, a non-trivial solution for this A x is equal to lambda x exists only when determinant of A minus lambda I is equal to 0. So, that is when I take this lambda x to left hand side. So, this is what I get, A minus lambda I times x is equal to 0. So, the solution of this, when I say non-trivial, that means I am looking for vector x which is not a null matrix, not a null vector. So, for a non-trivial solution, so x cannot be a null vector, then the only way this equation can hold is when this matrix becomes singular, and that is when determinant of A minus lambda I is equal to 0. So, when we expand this determinant, so this will be an nth degree polynomial in terms of lambda. So, there will be n number of roots of this polynomial, nth degree polynomial. So, those roots of this characteristic polynomial, this is called as the characteristic polynomial, and roots of this characteristic polynomial are known as, are referred to as the eigenvalues. Eigenvalues are the roots of this characteristic polynomial, and once we find a particular eigenvalue, we can substitute it back in this equation and then compute a corresponding eigenvector to a degree of scale, I mean constant of proportionality. So, we can shape, we can find out one particular eigenvector for I mean if x is an eigenvector, then alpha times x is also an eigenvector of the matrix. So, it can always only be determined to a constant of proportionality. There is, so eigenvector is not unique, because this matrix A minus lambda I is of course a singular matrix. So, there is no, there can't be a unique solution to this. So, there has to be a constraint, additional constraint before vector x can be calculated, and that constraint is by imposed by assuming some value for one of the elements or to couple of the elements, depending on what is the multiplicity of this eigenvalue, and then the rest of the elements of this vector can be calculated. So, and that is why it is not possible to say that we solve for this system of equations, because this system of equations is still singular, and constraints have to be imposed before we can compute the eigenvector. So, standard eigenvalue problem is referred to as A x is equal to lambda x. So, there is only one square matrix A, and x is the corresponding eigenvector, which results after multiplication by A into a scaled version of it. Or we can have vector multiplying from the left side. So, their form, that form becomes y transpose A is equal to lambda times y transpose. So, this is also an eigenvector. So, these are referred to as here x operates on the right hand side. So, this is referred to as the right eigenvector, and here y operates on the left side of the matrix A. So, this is referred to as the left eigenvector of matrix A. If matrix A is symmetric, then obviously there is no difference between left eigenvector and right eigenvector, they are identical. So, x is called right eigenvector and y is called the left eigenvector, and for a corresponding to a value eigenvalue, specific eigenvalue lambda, and these can be interchanged. I mean left eigenvector of A is the right eigenvector of A transpose and vice versa. So, that is a simple mathematical operation. If we take the transpose, then the result is arrived at. And for symmetric matrix A, left and right eigenvectors are identical. So, this is as far as standard eigenvalue problem, what is referred to as standard eigenvalue problem is concerned. Now, we can also have a generalized eigenvalue problem. For example, in this case lambda, instead of lambda x, what we say is A x results into another vector which is lambda times b times x. So, there are two matrices here. So, A x results into a scaled version of another rotation of matrix of vector x. So, A x is equal to lambda b x, or y transpose A is equal to lambda times y transpose b. So, that is generalized eigenvalue problem, and obviously, there is not I mean lot of similarities between the two. Generalized eigenvalue problem can be converted into standard form, or standard eigenvalue problem can be considered as a special case of generalized eigenvalue problem, where matrix B is identity matrix. And here if we pre-multiply by B inverse, then this generalized eigenvalue problem actually reduces to standard form. So, it can be readily converted to standard form as B inverse A x is equal to lambda x for a positive definite B, for matrix B. Now, the trouble with this is B inverse A is not necessarily symmetric, even if both A and B are symmetric. Now, the reason for symmetry is very important. It is not just limited to the storage, because if it is if A and B are symmetric, then we can get away, or we can do all the computation by storing only about half of the matrix. We do not really need to store other half, I mean lower diagonal lower triangular portion of the matrix, right. So, that results in considerable saving in the storage space and resulting into more compact storage. But if we pre-multiply by B inverse, then this symmetry may be lost. Even if A and B are both symmetric, B inverse A is not guaranteed to be symmetric. So, that is another reason why pre-multiplication by inverse is not really a good idea and not really required as well. The preferred form is to since B is considered to be positive definite and it is symmetric. So, its decomposition is going to be LL transpose Cholesky decomposition. So, once we have this, then this B inverse can be easily converted into this particular form. So, this entire algebraic equation, this standard eigenvalue I mean generalized eigenvalue problem can be referred to as, let me just say, A x is equal to lambda B x. So, if B is equal to L transpose, then I can write this as so this I can write it as right. So, L inverse is easy to compute, that it can be computed using simultaneous equation. I mean the triangular system of equations can be solved for multiple right hand sides, which is equal to identity matrix, and inverse of this triangular matrix L can be easily computed. So, that is what we arrive here, I mean L inverse. So, and this is of course identity matrix. So, we define assume this to be like this. So, we define another vector x hat, which is given by L transpose x, and that defines new problem x hat is equal to lambda times x hat. And if I write this as A hat x hat lambda times x hat. So, this becomes the standard eigenvalue problem, which has the same eigenvalue. Eigenvalue is same as the original problem. Eigenvectors are related to the original eigenvectors through L transpose x is equal to x hat. So, once we compute x hat, we can recover the original eigenvector corresponding to the original problem from this simple relation that x hat is equal to L transpose x, and solving this system of equations we can compute the vector x, desired vector x. So, this is how the transference conversion of generalized eigenvalue problem into standard eigenvalue problem format is actually implemented in practice. It is never done as B inverse A. So, that is what we are referring to here. So, preferred form is L inverse A L transpose inverse x hat is equal to lambda x hat. So, that becomes alternate form, I mean how a generalized eigenvalue problem can be converted into a standard form. So, why is it so important? Why is eigenvalue problem so important or so prevalent in different fields? One thing is we have already seen several instances all through this course. We have seen the importance of knowing the basis defining the basis of an n dimensional space or vector space. So, knowing the proper basis to expand or to analyze any vector or to solve any problem is very, very important. Now, finding a suitable basis is not a very easy task except for constructing the basis for Euclidean Euclidean vector spaces, where the unit vectors are the basis. So, 1 0 0 0 0, 0 1 0 0 0 0, 0 0 1 0 0 0 0 and so on. So, Euclidean unit vectors, they form they are very easy to construct and they can be generated, but while they are easy to generate, they are not really very convenient to simplify the problem, and many a times eigenvectors that we have, because these are derived from the operating matrix of the problem. So, they often offer considerable simplicity to the problem being posed. So, it is possible to transform the problem into a much simpler form by using the transformation of variables, where eigenvectors of the matrix, they serve as the basis. Now, why is it so convenient, or why the eigenvectors form a convenient basis? It is because of the very interesting property that eigenvectors form an orthogonal set of base vectors, or they are mutually orthogonal to each other. So, if I compute, I mean, there are, as I said, there are different eigenvectors corresponding to different eigenvalues. So, one matrix can have several eigenvalues, those are the roots of the characteristic polynomial. So, for each eigenvalue there would be a corresponding eigenvector. Now, what we are trying to say here is, as long as the eigenvalues are distinct, that is, two eigenvalues that I am looking at, they are different from each other, they are distinct, then the eigenvectors are orthogonal to each other, and that is a very, very powerful property. And orthogonality is always desirable, that always leads to a very efficient transformation system, because for an orthogonal matrix we do not need to compute the inverse, its transpose its own inverse. So, that we have discussed earlier when discussing the change of coordinate system or change of basis. So, the transformation between one basis to another basis, if it is related through an orthogonal matrix or orthogonal set of column vectors, then it becomes moving from one basis to another basis becomes very, very efficient calculation and very, very stable numerical operation. So, let us look at this orthogonality of eigenvectors in little detail. So, right eigenvectors x I corresponding to an eigenvalue lambda I is orthogonal to the left eigenvector y j corresponding to the eigenvalue lambda j. These two are different, lambda I is different from lambda j. So, that means y j transpose A x I is equal to 0, and of course, it also means that y j transpose x I, that should also be 0. If this is 0, then the other way around is also possible for all I not equal to j. Now, for symmetric matrix A, this is actually, this reduces to the same set of vectors, x I is same as y I, left eigenvectors are same as right eigenvectors, but this is the general statement. If A is unsymmetric, or then this is the general rule that left eigenvectors are orthogonal to right eigenvectors, and this has immense practical utility as a convenient basis to generate an orthonormal basis set of basis vectors. And decomposition of matrix by rank 1 updates by orthonormal eigenvectors. So, because y transpose x is equal to identity matrix. So, if I collect all eigenvalues and eigenvectors in a common form, so A x, x is the column of eigenvectors, and lambda, this is the diagonal matrix of all eigenvalues. So, this is the in essence statement of all n number of eigenvalues and corresponding eigenvectors. So, this is for right eigenvectors and this is for the left eigenvectors. So, y transpose A is equal to lambda y transpose, or if we can multiply this by y transpose, post multiply y transpose, then it becomes x lambda y transpose is equal to A, because x y transpose is equal to of course identity matrix. And then we have this A inverse can be easily converted to, because A inverse of matrix A can be easily converted by this matrix, because lambda it only involves, because x and y they are orthogonal with respect to each other. So, their inverses can be easily computed, they are given by respective transpose matrices, and inverse of lambda, that is diagonal matrix. So, that is also easily computed. So, this is very inverse computation of inverse by using eigenvalue expansion is a very simple rank 1 update. So, this actually implies if we expand this in terms of summation of these vector products, then each term, there are n number of terms here, and each term actually contributes to one rank, building up one rank of the matrix A, complete matrix. So, A if A is full rank matrix n with rank n, then n number of terms, each of these terms will actually add one rank to the system. And this validation of mathematical model A or A inverse of the system by reconstruction by using experimentally determined eigenvectors and eigenvalues. So, this is a very useful tool for reconstruction of the matrix. For example, system flexibility matrix can be structural flexibility can be constructed by observing some eigenvalues and eigenvectors from the vibration data of this structure, and using those flexibility matrices we can draw useful inferences about the health of the structure. So, these are all applications that are possible, and hence these tricks, I mean the eigenvalues and eigenvectors, the importance of eigenvalues and eigenvectors in constituting or in giving the orthonormal basis is very crucial in simplifying the problems and even finding new insights into the problem. So, now how this actually works, or what is what happens when we multiply eigenvector matrix with a vector. And remember in last lecture while discussing conjugate gradients, I had discussed that in Krylov subspace we have the matrix, we have the subspace or the Krylov subspace, elements of the Krylov subspace are given by R 0, then A R 0 and A square R 0, A cube R 0 and so on. So, higher powers of A matrix A are involved, and that is what gives us new directions with each iteration. And there we said that for higher powers of A, it is possible that the vectors may begin to lose their independence, and that we will see now why that will happen, why that can happen. So, what happens is, if x is the original vector and it is multiplied by A, so it is rotated like this, and let us say phi 1 and phi 2 they are two eigenvectors, right. So, of matrix A. So, if there are two eigenvectors, then they constitute the basis, because they are orthonormal vectors. So, I can use them as a basis vector to expand the any arbitrary vector. So, vector x here can be expressed as C 1 times phi 1 plus C 2 times phi 2. Phi 1 and phi 2, they are two eigenvectors of matrix A corresponding to the eigenvalues lambda 1 and lambda 2. So, A times x will refer to A times C 1 phi 1 plus A times C 2 phi 2, and A times phi 1 is of course equal to lambda 1 phi 1, that is the by definition of eigenvalue problem, and A times phi 2 is going to be lambda 2 phi 2. So, that is what we have. So, A x will be equal to lambda 1 C 1 phi 1 plus lambda 2 C 2 phi 2. Now, this is what we look at it. So, lambda A x, so this is vector C 1 phi 1, this is what makes it. So, vector x can be decomposed as a combination of resultant of this C 1 phi 1 and C 2 phi 2. So, this is what vector x is representing, resultant of this C 2 phi 2 and C 1 phi 1. Now, after multiplying with matrix A, it results in lambda 1 C 1 phi 1. So, this contribution increases by lambda 1, gets scaled by lambda 1, and this component gets scaled by lambda 2. So, lambda 2 C 2 phi 2, resultant is A x, and if I multiply with A again, then it becomes A square x, which is resulted by lambda square C 1 phi 1, because this will again be equal to lambda 1 C 1 A phi 1. So, that will be equal to lambda 1 phi 1. So, that will be lambda 1 multiplied by lambda 1. So, lambda squared. So, lambda squared C 1 phi 1, and similarly here it becomes lambda 2 squared C 2 phi 2. So, gradually as we keep on increasing multiplying with A repeatedly, what will happen is this matrix or this vector A raised to the power n, let us say some higher power of matrix A, this vector will be aligned, will tend to align with phi 1. The components of phi 2 will be subsumed. I am of course assuming that lambda 1 is greater than 1 and lambda 2 is smaller than 1, which will happen some of the cases, I mean relative speaking. So, if lambda 1, I mean lambda 1 is much larger than lambda 2, then gradually this multiplication will align with the dominant eigenvalue and corresponding eigenvector. So, this is what it means. So, what will happen is for higher powers of A, this will, all these vectors will tend to be very close to the eigenvector corresponding to the dominant eigenvalue of matrix A, and that is why the vectors in the Krylov subspace begin to lose their independence for higher powers of A, and that is why it is required to make them orthogonal by using Gram-Schmidt orthogonalization after a while. So, this is basic idea of the matrix vector multiplication. By successive multiplication of the matrix, we can nudge a vector to align with its dominant eigenvector. So, we consider a second order matrix, so 2 by 2 matrix, and the eigenpairs are lambda 1 phi 1 and lambda 2 phi 2. The set of eigenvectors phi 1 phi 2, they constitute a valid basis to represent any arbitrary vector x as a linear combination. So, that is why we can write x is equal to C 1 phi 1 plus C 2 phi 2, and multiplication by A rotates the original vector x by scaling of the components along the eigenvectors. By what I mean by scaling will be by the corresponding eigenvalue. So, phi 1 is scaled by, phi 1 component is scaled by lambda 1, phi 2 component is scaled by lambda 2. And this actually hints at the first algorithm for computing eigenvalues and eigenvectors. We just keep on multiplying. whatever we start with a vector, any vector, it could be any vector, we multiply with A, again this new vector that we get, we multiply with A, new vector we get, we multiply with A, eventually it will align with the dominant eigenvector, as we see here in this graphical picture. Graphical, I mean gradually x, we started the x somewhere here and the first dominant eigenvector is aligned here. So, this dominant eigenvector, so this vector x can be nudged towards dominant eigenvector by successive multiplication of matrix A, and that suggests us the first algorithm to solve for, to find out, to compute the eigen spectrum, the complete computation, complete representation of eigenvalues with eigenvectors, that is referred to as the eigen spectrum. So, this is what we refer to as the power law or power of scaling. So, successive multiplication by A rotates any arbitrary vector x naught progressively to align with the eigenvector associated with the largest eigenvalue. Now, the only thing that we need to do is we need to scale them after each multiplication, after each matrix multiplication, so that we can detect the convergence. Otherwise, it will keep on increasing by a factor of lambda and it may not be easy to detect the convergence. And as I said, this is the loss, this is the reason for loss of independence in search direction in the method of conjugate gradients for solution of simultaneous equations. So, let us assume x 0 as a linear combination of basis vectors, eigenvectors as the basis. So, sigma I equal to 1 to n summation over I C I phi I, n number of terms. So, when I start with starting with x 0 as the trial vector, first vector x 1, if I multiply with a x 0 and then divide it by some let us say some number, let us say it is, I call it as lambda max. So, that is the maximum eigenvalue, it can be some any number some. So, if I scale it by this number, so lambda I by lambda max. So, each term would be scaled by this lambda I by lambda max. Lambda max is the highest, largest eigenvalue. So, if lambda max is largest eigenvalue, then lambda I by lambda max is obviously going to be less than unity, and there will be only one term which is going to be unity, that will be lambda max by lambda max. So, whichever eigenvector that lambda max corresponds to, that term will have coefficient of 1, all others will have coefficients, I mean this ratio of eigenvalues less than 1. And for this repeated multiplication of matrix A, this ratio will obviously diminish with positive powers with every iteration, and any ratio, any number which is smaller than 1, less than 1, and if we keep on repeatedly multiplying it, its value will obviously diminish, it will approach 0. So, for large p terms with lambda I, so eigenvalues, ith eigenvalues, lambda eigenvalues with smaller than lambda max will be annihilated, they will be suppressed, and eventually we will be left with only one term that is corresponding to lambda max, and that is why the power iterations, this is called power iterations. So, by virtue of the power of multiplication, repeated multiplication, any trial vector, starting with any trial vector, we can converge to the eigenvectors associated with dominant eigenvalue, the largest eigenvalue in magnitude. So, this is the first algorithm, but we computed the eigenvalues and eigenvectors, I mean the dominant eigenvalue and eigenvector corresponding to dominant eigenvalue, but what next? This is just one of the n number of eigenvalues and eigenvectors, and quite often it is not the highest eigenvalue and eigenvector that is of interest, rather it is the other way round. So, lower end of the spectrum is of more interest for engineering analysis. So, how do we compute that? How do we go about with that computation of rest of the eigenspectrum? We will discuss in our next lecture. Thank you.